stands for apparatus. Okay. So many people don't know. SLA means A is apparatus because it was considered to be a lab equipment, to do something. They never had vision to call it as a production system, right? But it became one. And that's the kind of disruption it has brought in some sense. So ASME or ASTME and all, they formed a group to segregate these, and they call it as BAT photopolymerization or photopolymerization, just like that. And you can see through this small animation, you're able to see the operation of this. Hello?
Hello, Mr.
Is it boring you all?
Mr.
You need a
No,
break?
not at all.
You need a break?
Mr. Ashutosh, please. No, sir, we can continue. Mr. Ashutosh, please mute your mic. Mr. Ashutosh. Mr. Ashutosh. Mr. Ashutosh, Kashmiri, you can mute. Kashmiri.
सांगा म्हणलं मॅडम
MIS manager Kashmiri.
तुम्ही कॉलेजला जाणार आहेत आज तिकडे ते द्यायचं तुम्हाला कॉलेजला.
Mr. Ashutosh, please mute your mic.
एक काम आहे राजेश शिवाजीमध्ये जाऊन राजेश संध्याकाळ कोण राहील सेक्युरिटीला देऊन टाका.
This is something like students doing with us.
मला बी घेऊन दे होती घेऊन दे रे बाबा जगू मला बी घेऊन दे.
Host can actually.
Yeah, host. I'm connecting with host. Let me just give a minute, sir.
आनंद नाव टाकून ठेवा सर त्याच्यावर नेटवर देऊन टाकेल.
देश पांडे नाही संध्याकाळी हो आता नाही संध्याकाळी गेले ना फक्त सिक्युरिटी गार्डला देऊन टाका. आपण काय करू उद्या नाहीतर ती बाई रात्रभर दिमाग खाईल आपलं.
नाही नाही आता फोन करून सांगून देऊ संध्याकाळी दिले.
Sir, administrator has the right to mute any participant, so I would request administrator if they can mute.
I think it has subsided. I'll start, let us. And you can see this liquid, when you're ejecting it from the table, it looks like this. These are crystallized, the photo polymerization from a monomer liquid. It transforms to a cross-linked monomer, becomes a polymer, right? And so beautiful. And next technology is powder bed fusion, and the inventor called it as selective laser sintering, SLS. Okay, and it's quite popular and most dear to me because you can create something impossible using this. Let us see how it looks when we do the animation. So there is a powder and there is a rolling pin that will spread the powder on either side, to and fro, right and left, and subsequently the layers are all sintered, and the sintered layer goes down. Okay, let us take a closer look of that. The powder particles are bound together, at the contact point. They get a kind of a Docker welded, and because of CO2 laser with a Gaussian distribution of power, it not only stitches the top layer, but also it will stitch to the bottom layer. Okay, and thereby making a very sound object. And you can see it could be a little bit porous here. This happens with nylon, and when you work with metal also it can happen. So when you increase the power of laser, you're going to use a fiber laser there. It is going to have a melt pool, that we'll see in metal. Okay, and so this is how a CO2 laser will bind the layers to make the object. So you can see here on the left hand side you have a concentric circles getting formed. So that is sintering. The laser is binding the powder, and the powder becomes a kind of sheet like thing there. And because there is a one more layer of powder coming again, rolled and compacted, and laser is again acting on the same place, the whole thing becomes a concentric cylinder or a tubing, or whatever, section. At this section, it is looking like this, but it can keep changing. And then you kind of eject the whole thing and extricate these things like excavation of archaeology. The parts are hidden inside. You uncover them, removing the loose powder off, and by this we can actually create objects that are what I can say. I'm sorry. Objects which are interlinked or assembled, or which are nested also. One inside the other can be done, because you can shake the powder to remove. And powder here acts like a support, and we can play around with the tolerances of two parts which are moving, having a relative motion that can be brought about. Because in CAD, there is no gravity. You can play, we can keep anything suspended. You can take a sphere and put another sphere inside, another sphere inside in a CAD, because in CAD they stay. It is like there is no gravity in CAD. When it comes to 3D printed also, it will behave as though there is a zero gravity, because powder is supporting it, all the place. And when you remove it, when the powder falls off, then only the effect of gravity starts, acting on it, and they fall one inside the other. So people will be wondering how this went inside, or how this link happened. How anybody went and assembled it. It's because you have already done it in the CAD itself. It's an assembly which is going inside, and for this car, for example, or a Jeep, the wheels move because there is a relative motion that has been maintained. And when you are exporting it, you don't necessarily take it down, but they are concentric, like a floating. And once it is getting printed, the same thing, the powder in between will fall off, thereby you're going to achieve. Hope I got it. And so the next technology is FDM, the fused deposition modeling. Some people call it as free-form fabrication also. And the Stratasys, the company, on the right-hand top, you have that system. You have a low-cost one in the foreground, and it's a printer, a Chinese-made printer. And each of them have a huge difference in price. But what they produce is same quality, only difference is in the top one can expect this to work 24/7, 365 days, and you want it to print, it will always print. So what we are talking about is the reliability of system. Okay, whereas the one in the foreground, the red model, what you have, probably it may work today, it may not work tomorrow. I mean, you have to make it work, So reliability is the issue, but they produce. If they produce the same kind of material. That means here, probably the company did not sufficiently innovate. The Stratasys people. It became open source, and today people have not only taken it out and improved upon it. That is the beauty of it. So what you see here is a MakerBot. In fact, MakerBot was the first open source commercial machine which came outside Stratasys. Later on, Stratasys kind of bought it over. It was like killing the competition there. And of course, we have another technology called LOM, is laminated object manufacturing. A company called Halisys used to do it with a laser, what you see here on the left-hand side. But they could not actually make enough money. It became bankrupt. And on the right-hand side, you have MCore. This is an airline company which started using a kind of blade to cut a paper. and they were also promoting as a biodegradable one because it uses paper and all that. Somehow they could not actually sell well because industry cannot adopt it. It is not a durable material, and the glue is again making it not recyclable. So whatever promise they did, though it can make a very juicy orange, what you see in the bottom left hand side, right hand side, this can be made as a model, but it has no other application other than display model. So it can be used in medicine, it can be used in teaching purpose, toy making, etc. But it doesn't have an industrial application as such. Okay, and that's why this company, MCore, also got shut down, and there is a new company which has come, again with the same new avatar. Then comes the MIT world. MIT America, they were also looking at this, how to make this technology. They were very close to the analogous selective laser sintering, that is SLS process, what they developed in Texas University. Here, they developed something. They were not using a laser to sinter. There was no sintering here. In fact, it's a cold process almost. So they had gypsum powder and they spread some gum adhesive, and the adhesive, after touching the powder, kind of absorbs powder and becomes a hard mass. And if you can spread one more layer, again I am going to stencil some kind of glue. You say print head. The print head will print glue, not ink. And when you print the glue, you spread the powder, the glue will absorb, and that this thing is kind of sintered. So sintering per se by laser is not required here. So beautiful, no? So it's called as binder jetting. Binder means binder is adhesive, adhesive. Because of adhesive, it is going to become a solid. So it is not polymerization, it is not sintering here, but adhesive action. And this particular thing they called as 3D printing. So much so, they are trademarked. So MIT technology was first to be called as 3D printing. Okay. For a long time, they were sticking to that trademark. But later on, when world started calling everything as 3D printing, they somehow gave up their rights. And so even today, we call it as 3D printing, thanks to the term actually coined by MIT. And it was for binder jetting. You should know historically. And you can see here a demo of how this wonderful technology works. The powder is first spread. So when I spread the powder, it is like a paper only. On paper, you can have a plotting or anything. And if you do the plotting, and you normally think of only 2D. Here, because it is going down every time, you can see the whole building comes out. When you vacuum the powder off, you'll be able to see the building emerging out, like a magic. So this same thing happens in SLS also, only with the difference, this is binder jetting, that is selective laser sintering. There the action is by laser, here the action is by binder. Binder means glue, adhesive, right? We can try this, in your colleges, you can try this. You take a atta or anything like that, you put some glue, take a stencil and screen print a glue, take it out, again spread one more layer of atta, again you put glue, so you'll be getting same thing. In fact, selective laser sintering was also done same way, putting powder by hand on all that, very funny. And that's what coil decoy did, and probably that's what they did in metal also. Much later, they all mechanized it. Now it has become a machine with all the things. Yet another wonderful technology is metal jetting, wherein you're for the first time able to create a kind of a functionally graded material. That means I have component A and component B. I can mix them in varying proportions, and I can the target, the end result is either I can have more of A and less of B, or more of B or less of A, or equal A and equal B. So I can play with things like in a same component, one side transparency, another opacity, one side hardness, another side softness. One can achieve, you know, that kind of So they call it as a digital material. Why it's called as a digital material? Because I'm able to by computing and programming, I can specify what is the hardness, what is the transparency I need for that particular small 3D pixel. 3D pixel is called as a voxel. You know, in that particular small cuboid, what property I want to assign, I can actually program it. And so, and this is also dispensed by automation. And so we call it as a digital because it is all controlled by zeros and one of computer programming. The term digital material was born. And this company, Object, was a Israeli company later on taken over by Stratasys. Today they're part of the Stratasys team. And it's a wonderful technology. Somehow, still they need to work on it, you know. It is not, though it's very good, very expensive. And in fact, if I were to tell, tick which is the most developed, best 3D printing, I will say this one, material jetting. Why? Because I can make a part, you know, all at one place. You know, I don't have to have a O-ring. You can see O-ring, soft O-ring, and the half white manifold on the actuator, which is soft to touch but hard inside. That kind of, material, it's a composite, you know, in a way, it's a composite material, which is because of the various permutation combinations of the mixing of A and B, or maybe C, is possible at the click of button, you know, by programming. I think this is the best one can look at, you know, 3D printing as. In fact, human body, you know, we are all produced with in the mother's womb like this. We have hati, which is very hard. And, you know, we have soft muscles and all. We have bionic eyes, CPU, brain, all that, you know. And nature is nothing to, nature is the best designer. Again, a connection from the term design. Nature is the best designer. Whatever we are trying to imitate, mimic, is in a way looking at nature. You know. So people, same thing they follow to bioplow printing also. They say we can print organs the same way, you know, they're simulating. You fake it before you make it, kind of thing. And you can see in material jetting, actually the consistency is like a paste, you know, toothpaste, you know. So they put it on the substratum, and it is exposed to UV light. So it's a photosensitive paste, a photopolymer paste, I can say, you know. And so it is material jetting here, not binder jetting, material jetting, because material is getting deposited and UV light exposure makes it set. So it locks it. You know, there is no further reaction that can happen. And so that's, then we have, of course, the directed energy deposition is another major technology. In fact, a class of technologies go under this. Electron beam melting also. Electron beam melting, sometimes we classify under powder bed fusion also. So a lot of things there. SLM, you have UOS having the DMLS. They're all one and the same. Different semantics, that's all, in a way. And people are nowadays they're even trying to use feedstock as wire, metal wire. And the metal wire technologies are going to really disrupt compared to the powder-based ones. And you can see in the metal how the whole thing, the powder gets molten, and this molten metal means the specific gravity is higher than the powder. The whole thing sinks. So in metal, supports are very important. They are absolute must. There are exceptions there, but because of which it also complicates, polymer printing to 3D print, metal 3D print. You can see here DMLS how metal is getting sintered with a fiber laser, and the sintered areas have become a sheet of metal. They're all surrounded by powder, and this powder is not capable of supporting like in SLS, because the melt pool is heavier than the powder specific gravity. It will start sinking or it will start shifting, and the temperature, as and when it gets deposited more and more, the heat capacity also increases. So the thermodynamics of it, heat and mass transfer of it, and the stability, so many things, and the mechanical heat affected zone, and this heat have to be taken out quickly. So heat scavenging, what we call, this is all going to be very important, when we move. And so people have tried to use powder or wire, to take it to a tip with a laser beam, and when the powder come, the whole thing melts, and you put a drop, on the subtractor. It's called drop on demand kind of thing. So using many drops, you are able to actually make the whole entity apart. So this is very interesting because this can convert any CNC into a metal 3D additive. I will show you some, maybe tomorrow next talk, I'll go a little deeper. These are some of the metal printers we have. And look at this. So far we have been looking at all these boxes, they're all boxed. So far we have been seeing boxes. Now you see something which is out of the box. This is a KUKA robot, which is a general purpose robot, which can be programmed in multiple ways. And what people have done, they have put a kind of big syringe, and they have a magazine feed of clay, a red clay, and it is getting deposited. And the data is actually read from a computer, So, question is, can we call it as a 3D printer? Yes, this is a 3D printer because it can create entity, and it is building layer upon layer, and it is getting the whole input from a digital data. In fact, it is out of the box 3D printing. It can print not only in that station, but all around it. It can, so if you are thinking of a food printer, so it can make something, food, and that becomes ready, and the next, it can go to the next station, the next station, like that, all around it can move. So I think the robots have the highest dexterity, and we can see a lot of future 3D printers will be based on robots. And look at this is a 3D doodler. So my question to all of you, whether we can call it as a FDM printer, you can unmute and answer this question. Can we call it as a FDM printer?
Yes, sir.
So how many of you say yes, along with you?
Yes, sir. Yes, sir.
Well, no, it cannot be called as a 3D printer because there is no digital input data. Okay, it behaves as though it is a FDM printer. It is like a glue gun. It is like mehendi lagate, I say, and it is no doubt depositing layer by layer. Forget it. It need not be always layer by layer, but digital input data should be there. If it is not there, then you can say it is not 3D printing. Got my point? So the hands are there, and you have got a thinking in the brain, and it comes, and you are forming something. that cannot be called as a 3D printing. So you can see how it is being done. But what happens if this hand is replaced by a robot? Can we call it as a 3D printer? What if I replace this, the hand by a robotic actuator? Then we can call it as a 3D printer. It becomes like a same thing as your cooker. So let us see one example. See this one. This is, in fact, depositing not even on ground, against gravity. It is depositing something on a side wall. And believe me, even this can be called a 3D printer because it is getting a digital input data. It can make one, it can make 100. It doesn't get tired, and you can check the consistency also. It is going to be same. So you can see how robotics are actually changing the way we look at 3D printers. In fact, it is additive but not printing many things in this world. Moti hai, moti is additively made. Onion hai, onion is additively made. You have so many things like that. Wood, you cut a wood, big tree. You have annual rings there. Why? Because the girth is increasing every day, every year by organic means of material deposition, right? And so this is additive, not 3D printing. So it's very important when you're going to take on creative students. It's important to understand this. Somebody may say, "Hey, this is additive, but it is not 3D printing." What is the example you can give? Laddu is there. Very interestingly, this also. Additive but not 3D printing. I want all of you to understand one thing here. Very, very important. There are so many slides here. Very much similar to a 3D printing. And at every layer, it is made up of so many layers. At every layer, I can put chutney, or I can put cheese, I can put jam, I can put ham, I can put, anything there, vegetables and all. So it changes. So, for example, if you take a casting, I cannot do the casting like this. To some extent, sintering you can do. But even sintering is difficult because after you have powder, you compact and you sinter it. That's it. You don't have to, not necessarily you can change the layers. But in 3D printing, I have a control over every layer. At every layer, I know what I can deposit. Isn't it? That is very important. By this, what we can learn is, in 3D printing, we have a capability to control what you deposit every layer. Depending on that treatment, what you give, it will change the property. For example, laser exposure also, power also, I vary. I can create different material property. And that is the beauty of additive manufacturing, which is not there in forging, it is not there in injection molding, it is not there in die casting, it is definitely not there in CNC. That is the greatest advantage we have with additive manufacturing. We are able to control properties at a layer. And I told you, digital material, you can even control the property at a voxel level. Voxel is a 2D, 3D pixel. And in fact, it is Adrian Boyer and his team, and they started, mooting this concept of parent and child. 3D printer printing itself. So the cartoons like this appeared. In fact, yesterday in Facebook, I saw something I want to show you. So manufacturer files for bankruptcy. Why? 3D printing company asked client not to print 3D printers. So if you are selling a product, using that product, you are going to create the same product again. Like what we saw here, the same thing we are able to see somebody has done. This is a Mojo printer. Some of you must be knowing Mojo printers. And so these are fun. I mean, it's not happening, but it may happen one day. In fact, we have a technology called multi-jet fusion, MJF. There, 50% of the parts are printed by the same machine. Can you believe it? More than 50%. So many rollers, gears, stoppers, many things are made. 50%, of the parts are from the same printer, printed on a similar technology. I can say it's not same. So today we have these consumer printers which are coming in all shapes and sizes, and the whole technology, once it got adapted, it's good, making deep inroads into various domains in manufacturing. It could be, aerospace, automotive, dental, electronics, jewelry, medical, FMCG packaging, lifestyle, architecture, automotive, aerospace, white goods, electronics, electrical, plastics, and many more. Gifting also, customization. It goes on and on. Food, you have cloth, you have what you cannot print is the question. So what you cannot print is the question. So what are these? These are truly unimaginable products, and also impossible to make products. Okay, but they're all possible today. Now, thanks to this technology. Now, at this point, I would like to stress upon the beauty as a industry person. What I say is 3D printing is used mainly for these 6 reasons. There could be many, but I consider them to be my top list. One is part consolidation. That means I can have any bill of material that can be squeezed to one item. So that's the capability. So you can make about 31 to 1, 50 to 1, 300 to 1, like that kind of zipping where one can do part consolidation. Part consolidation brings a lot of reliability to system because the variabilities are reduced here. And injection fixtures also, we can quickly make something on demand. That's why it is being used. Lightweighting is something which is very, very important. It is required for airborne systems such as rocketry, satellites, and the so-called airplanes also. And why not drones also, for example. Drones people are using, where payload is optimized by reducing the total, dead weight of the equipment. That is done by lightweighting. So the strategy is to go for organic forms, and these forms can only be printed. They cannot be done by any other way. Coming to complexity wise, jewelry is one of the most complex when it comes to manufacturing. So people are looking at it, and it has disrupted the jewelry making to a large extent today. In the world, anything can be made smaller, big at a click of button. Right and left we can do by flipping, at a a split second. And so complexity is very high in jewelry, and for additive manufacturing or 3D printing, complexity is fine. Because it can handle at no extra cost. And world is also looking at one-off products, need for one part. Whenever you make anything one part, you cannot be always viable. But how can you be viable? Conventionally, it's difficult. But from additive manufacturing or 3D printing area, if we look at it, it is definitely possible to make one and be viable, affordable, and so it's very important. We do a lot of customized things where you require just one. For example, prototype also. Prototype, people will not make many. They take just one and they want to check it. And mass customization. Customization is something which is very high in patient-specific solutions. in medical, and so while it can act in any sector, medical sector stands to benefit most when you do customization for a particular patient. And we cannot call it as fabrication. No, we can call it as fabrication. We cannot call it as manufacturing because you're not making millions. You're just making one or two of what is required. That's it. So people have tried to print something big. People have tried to print something small also. And you can see, and the nanoscribe can print very small. In the bottom left-hand side, you have 20 micron green line. And that shows the scale, right? So what will be those verticals window on the top cheja on the window can be. It is definitely micron level, right? So people have tried to print big and they are also trying to print small. And what about this? The foreground you have a printer and the background you have a memo. How they have printed this? Well, by digitally cutting it and making into small blocks, they can put them together to get the whole part. Okay. That's how they have built it. So this is one of the greatest virtues. Many times you can digitally cut a part and glue it. Now you have Loctite and other stuff which are very good glues. So the industrial scale 3D printing will look like this: shop floor clean and cool, no dust, no oil. This is the future factory in a way. This we have been emphasizing, like your faculties in the morning also described this. There is complexity will come for free and there is no economy of scale. Because you make one number, 10 numbers, 100 numbers, 1,000 numbers, 1 million. The rate for one part will not change so much because it is a layer by layer deposition, right? It has to make so many layers, only then get ready for the... So it is very important. We cannot compare it with conventional manufacturing, subtractive manufacturing, when it comes to bulk production. But complexity wise, in conventional, more and more process go on, more and more you touch, you actually lose value. So people say complexity comes for free is not really always true, but in a way it is tapering off slightly. So where do we actually see this technology in the manufacturing world? So you can see the volume game is even today is done by only subtractive manufacturing or other forms of conventional ones, injection molding, die casting, or vacuum casting, like that. In the middle, you have a CNC, which is going to make few batch quantities, and 3D printing is at a very, very different place altogether. Low numbers, but highest complexity. That's where it will be viable. So in the earlier days, when the Czech Hull started looking at this technology, at the center of whole thing was the hardware. Of course, there is a little bit of the small piece of software to slice and conversion of the model to a triangulated model, STL, and material, some few materials. That's it. So the opportunity was more in terms of hardware, software and material. They were just complementing each other. That's all. But soon, today, it has changed. Hardware, software and material, they have a lot to have overlapping. And in future, the hardware will become mostly saturated and the hardware, once you say it's saturated, lot of me too kind of